Hi guys, welcome to chapter 7, which is all about electricity, electrical current, potential difference, and energy flow. Today we're going to be going through chapter 7.1, which is all about charge, but just a bit of an introduction about chapter 7. So we're going to be going through these key formulas, looking at electric potential, elementary charge, which is what we're going to be doing today, electric current, and electrical power. So we'll cover all of those formulas as we go through this week's content. So this chapter is all about some recall questions about electrical charge, electric current, and the law of conservation of electric charge. We're going to be defining what electric current is, what electric potential difference in a circuit is, and what electrical power is. We're going to look at solving some problems involving electric current, electric charge, and time, and recall that energy is available to electric charges moving in an electrical circuit, and we use the measurement of electric potential difference to measure that. Then we're going to look at solving some problems about electric potential difference, explaining why charge separation produces electric potential difference, and then solve some problems involving electrical power. So on to chapter 7.1, looking at electrical charge, not the charge of the light brigade. So some questions to consider before we get started. If you rub your head with a balloon, would your hair stay standing up or would it go back down after a while? If you've got a balloon laying around at home, you can try that out for yourself now. If you've got a trampoline in your backyard, you might like to go and jump on that. Tell your parents that you're doing a prac for physics. Why, when you get off your trampoline, are you sometimes zapped by a static charge when you get off it? So why do we think the first question is if you rub your head with a balloon, obviously your hair's not going to stay up forever. So when you rub your head with a balloon, you're transferring charge between the balloon and your hair. And because your hair then becomes all the hairs on your head become likely charged, they will repel each other, so they will stand up to try and get as far away from each other as they can. But obviously over some time, your hair would go back down to normal. So the reason for that is because the water molecules in the air or humidity cause the charge. They can absorb the charge from your hair and they can move it away so that your hair becomes back to being neutrally charged again. This is the reason why the Van de Graaff generator, if we're in class, we could use a Van de Graaff generator. It wouldn't really work on a day when it's particularly cloudy and rainy. It only really works when it's dry because the more humidity in the air, the more easily the charge is able to move away from the Van de Graaff generator rather than being built up on the dome. And why do you get zapped if you bounce on a trampoline? Because the synthetic material that the mat is made of, when you rub your feet or your clothes on that mat, then charge gets transferred from you into the mat, and then the electrons move down through the metal frame into the ground. And then when you go to get off it, you're left with a positive charge, so the electrons zap you by moving back from the metal frame up into your body to neutralize your positive charge. All right, so for chapter 7.1 today, we're going to be investigating the classification of charge as being both positive and negative charges. We're going to describe what conductors and insulators are, and you'll know that you're successful if you're able to explain the physics of what a charge carrier is and able to explain how elementary charge carriers make different materials conductors or insulators. So talking about electric charge, the electron was first discovered by J.J. Thomson in 1897. They were doing experiments. They knew that there was charge that could be transferred between objects. And when they rubbed a plastic rod with fur, that rod became negative and the electron had the same charge as that rod. So therefore they classified the electron as being a negative charge. Electrons are therefore considered to be particles with negative charge. We'll look in Unit 4 at the end of next year about some more weird properties of electrons, but just for you guys now in Year 11, it's enough to consider that electrons are just little particles with a negative charge. And electrons can be transferred from objects or in between objects. So if you removed electrons from a glass rod, say, then the glass would be left with an excess of positive charges. So static electric charges is all about the transfer of electrons either into or away from objects. and that causes the object to gain either a positive or a negative charge. Since the discovery of the electron, we've now found out that the protons are positively charged, and as we talked about in the nuclear physics topic, the number of positive and negative charges in the atom balance each other out. So up the top there's a definition from the textbook. Charge is one of the basic properties of elementary particles, which are protons and electrons, which can be positive or negative and occurs in whole numbers or discrete units. So why do you think that is? Why do you think the charge can only occur in whole numbers? Why can we not have a like 1.5 electron difference of charge between two objects? So obviously it's the fact that we can only transfer 1 electron or 2 electrons or 3 electrons or 57,000 electrons between two objects. We can't ever transfer fractional amounts of electrons. So therefore, when we're looking at the charge absorbed or the charge transferred between objects, we can only talk in terms of whole numbers of electrons being transferred. So the electron is the charge carrier. It's considered to be the elementary charge. So the charge on an electron is considered to be the elementary charge, and we use the units of coulombs with the unit of capital C to determine or to describe the amount of charge. So 1 coulomb of charge is actually a really, really large amount of charge. It's about 6.25 by 10 to the power of 18 electrons being transferred. So typically when we're talking about electric charges, we won't talk really in whole numbers of charges. So for example, like a lightning bolt is anywhere between 2 to 10 coulombs of charge. So a coulomb is actually quite a large amount of charge. So the table down below, we've got an electron, so we can say an electron has a -1 charge and a proton has a +1 charge and a neutron is neutral. But in terms of coulombs, an electron is -1.6 by 10 to the -19 coulombs of charge. A proton then obviously is +1.6 by 10 to the -19 coulombs, and a neutron has 0 coulombs of charge. The masses we talked about in the nuclear physics topic. It's not really very important for electrical charge and for electric circuits to look at the masses of those particles. We find the electrons in the orbital cloud around the nucleus, and obviously we know that we find protons in the nucleus. So to measure the amount of charge, so we can look at the number of elementary charges or the number of electrons which are transferred from one object to another, or the number of electrons excess or deficient that an object might be. So the number of elementary charges equals the total charge, capital Q, divided by the charge on one electron. So if I had a charge of 3 coulombs, I could work out how many electrons that 3 coulomb charge represents. So the example 7.1, which is on page 208 of your textbook, calculate the number of excess electrons in a charge of 2.5 coulombs. So using the formula N equals the charge over the charge on an electron, we have 2.5 coulombs divided by 1.6 by 10 to the -19 coulombs per electron. So we have 1.5625 by 10 to the power of 19 electrons, or 1.6 by 10 to the -19 electrons. Does that work with what I said before, that we can't have fractions of electrons being charged? Like, can I have 1.6 times 10 to the -19 electrons? Well, yeah, obviously I can, because 1.6 by 10 to the -19 is like 1, 6, and then 18 zeros after it. So that is a whole number of electrons. So pretty straightforward formula. There's not too much thinking that goes into using that formula. Just plug and chug it and you'll be fine. So the law of conservation of charge basically just means that charge, just like sort of energy, we can't create or destroy charge. We can just transfer it from one object to another. So if the example here, we have a silk cloth and a glass rod. Initially, there was no charge on either of those objects. They were both neutral. But when we rub the glass rod with the silk cloth, electrons from the glass transfer into the silk cloth, and that leaves the glass with a deficiency of electrons or a positive net charge overall, and it leaves the silk cloth with an excess of electrons or a negative charge overall. So it's only ever electrons that get transferred. We can't obviously transfer protons from the silk cloth into the glass rod to give it a positive charge. So electrons are the only thing that moves when we're transferring charge from one object to another. So let's just imagine that we've had 5 electrons have moved from the glass rod into the silk cloth. So we have a +5 charge left on the rod, we have a -5 charge left on the silk cloth, but the total charge overall is still 0. So why then do some materials conduct electricity and some insulate against electric current? So in a conductor, like think about what are some conductors you can think of. Obviously, they're pretty much going to be metals. So with a conductor, there are more elementary charge carriers or more electrons that can move around through the crystal lattice of that material more easily. But with an insulator though, things like glass, plastic, rubber, they're all very good insulators because the electrons are really, really closely bound to the nucleus. So we know that the metal atomic structure has a sea of delocalized electrons which are able to move around much more easily. So there's some further reading you can do there. You can go and have a look at some things about Van de Graaff generators. So Van de Graaff generators are pretty cool. They just build up massive static electric charges around themselves, and then they discharge that through some grounded object. In this case, it's like a guy standing inside a big metal bird cage. So go and have a look at some Van de Graaff generators on YouTube. They're always pretty cool to look at. I've assigned some work on Education Perfect on Chapter 7, and there's also some work assigned for everybody on CK12 for Chapter 7. Those of you that haven't signed up for the CK12 Year 11 2020 physics class, please make sure you go and do that ASAP, because we will be assigning you guys work from CK12 pretty much every week. Education Perfect is available for the first 2 weeks of this term. Whether that gets extended or not, we're not sure just yet. So CK12 will be free and available for the entire time that we're learning online. So please make sure that you have gone and signed up for the CK12 Year 11 Physics 2020 class. So on both of those online learning sites, you've got some notes and lessons that you can go through, and then there's some practice quizzes with all of those. Obviously, the first protocol should be Check Your Learning Chapter 7.1. It's on page 209, 210 of your textbook. Once you've completed that, then you can go and have a look at the Education Perfect lesson, and you can go have a look at CK12 if you need to get a little bit more practice with that content. So we've just completed the second formula there, looking at elementary charges. Moving on to Chapter 7.2, we're going to be looking at current and voltage next time.